one more time, a very warm good morning. Namaskar, Subha Munjane. It is lockdown time everywhere, but let it not be a lockdown time for our hopes, not a lockdown time for our preparation, not a lockdown time for our dreams. Let us keep all of them alive and let us be very positive. Stay home, stay healthy. Now, 3 sessions we have finished, and before starting our 4th session, viewers and friends, let me remind you, these are not the sessions for an integrated coaching. This is purely meant to brush up all the key concepts for our coming CET NEET examinations. So bear it in mind, we are not getting into the complete detailings and an integrated coaching, brushing up all the key concepts. And one more thing, it was a happy thing that got few calls from our students for clarification of doubts and all, and I do expect more such number in the coming weeks. Now, today's topic would be 2 simple but very, very popular topics like electric flux and potential. Now, to begin with, flux, which is nothing but the physical representation of an electric field. Right? Yesterday's class we have told field is represented by field lines, and those field lines are nothing but electric flux. Now here is our definition statement, which is the basis for all the solutions based on flux. Now here is flux, defined as a cross product of intensity vector, and this one is the area vector. Here when we say area, it is surface area, right? This is a cross product of intensity vector of the field and surface area of the given surface. We are taking it as a dot product, therefore it is a scalar quantity. We are writing it as E magnitudes, E and A, and cos theta. The most important thing is about this theta. Theta is the angle between E bar and A bar. How to take that A bar, the aerial vector, a pseudo vector? So for that, you can look at this figure. Here I have shown, in the blue line I have represented, you can see I think, this is a blue line, a vector representing E bar, intensity vector. And now look at this vector. This is the surface I have considered, and for this surface, this is an outward normal. Remember, this is outward normal that represents aerial vector. Now, theta is the angle between normal drawn to the surface and the field vector. Remember, theta is not the angle between field and surface. It is angle between field and normal to the surface. Of course, I have not got into the details like SI unit. Or SI unit, other day we have told it is volt per meter, and this is area meter square. It becomes volt meter will be the SI unit. Now, another important thing is regarding the sign convention of flux. Here we have taken inward flux is always negative. Inward flux is always negative and outward flux is always positive. Supposing it is the flux entering into the surface, in all such cases the flux is negative, and in the case, let me show you diagrammatically over here. Can you please see this figure? Supposing this is some given surface, or let me take for that matter a sphere. And a sphere, I show the flux like this. You can see there outward arrow, you can see outward flux, then it becomes positive flux. If this flux is directed inwards, it will be a negative flux. Because whenever we are calculating the net flux, we have to use flux with a proper sign. The inward flux and outward flux, and hence net flux will be an algebraic summation. And regarding electric flux, the important concept is Gauss law. Gauss law always defined for closed surface, which we call Gaussian surface. Please go through your notebooks, we have given the detailings of Gaussian surface, the properties and all. So now Gauss law, which is applicable for closed surface, the statement here I have shown. The flux linked with a closed surface is given as an integral E bar dot dA bar. Why we have taken here the calculus form? Because this is applicable for both planar and non-planar surfaces. Curved surfaces, flat surfaces, we can make use, and that is why we have taken it as a calculus form. And here you can find this is 1 by epsilon naught times Qi, and this Qi refers to the net charge enclosed by the surface. Remember, this is net charge enclosed, that is the charge present inside the closed surface but not outside the surface. To understand what do we mean by this inside and net inside, here one more time I will show. Supposing this is some closed surface, a sphere, a spherical, or any other 3-dimension geometry. Remember, when we say closed surface, it is always 3D geometry. Now supposing this is an enclosure with, I will take some 4 microcoulomb positive and then minus 1 microcoulomb negative and 5 microcoulomb positive, like this. Now the net charge, and one more time, supposing if I take plus 2 microcoulomb which is outside the enclosure. Now when we are making use of this expression, this is plus 4 plus 5 minus 1, which brings out 8 microcoulomb positive, right? Whereas in this calculation we should not consider any charge which is outside the enclosure. Now when we use examples for flux, it will be asked either to calculate the flux through a surface, or sometimes even if it is asked like calculate the number of field lines. Number of field lines is nothing but flux. So same expression will be made use. Now coming to one more important point regarding flux. Now the flux enclosed by a surface, closed surface, depends only on the net charge enclosed by that enclosure. For any outside charges, there will be equal and opposite inward and outward flux, and therefore net flux will be 0. So it is only depending on the net charge which is present inside the enclosure. Please do take these 2 points very carefully, that it does not depend upon shape of the geometry and also does not depend upon size of the geometry. Only depending upon the net charge enclosed by this one. And one more example I would like to show for this E bar dot A bar. Now an example like this. A region contains an electric field. E bar is equal to some 25I minus 16J times 10 power 3, suppose volt per meter. Intensity vector given as a vector, and he says surface in, he says YZ plane, surface in YZ plane of area, suppose 50 centimeter square, 50 centimeter square magnitude, and he says that it is lying in YZ plane. Now how to take that dot product? See here. E bar is given straight away, as ijk vector, the position vector. Now how to write the aerial vector? Aerial vector says it is always outward normal. The given data says that it is in YZ plane. So which is the normal to the YZ plane means it becomes x-axis. If it is xy plane, normal becomes z-axis. Like that. If we make use of that, the data will be converted as E bar, no A bar. A bar is equal to 50 I because normal to YZ, therefore I am taking it as x-axis. 50 I, of course there is a multiple. Centimeter square is there, remember I am writing into SI units, 10 raised minus 4 meters square. And this is a very important suggestion we have been keep giving in every class. Be careful about the units. Always try to convert all the units into SI units. Now here I write E bar dot A bar. It's a simple dot product now. I dot I, yes. I dot I 1 and all other remaining terms will become 0. Therefore it is 50 times 5, 1, 2, 5, 0. And there is a multiple here, 10 raised 3 and this is 10 raised minus 4 which will give 10 raised minus 1 and the answer 1, 2, 5. And as I told you, it will be volt meter the unit. So that is how in calculating the total number of lines or flux with the proper sign convention. See, our next topic is electric potential. Electric potential we introduce in electrostatics for two analogs. We will use potential as analogous to temperature in thermodynamics or pressure in hydrostatics. Like there the heat flow is always from higher temperature to lower temperature, or the fluid flow from higher pressure to lower pressure. Here also in the case of charges, that flow is determined by the parameter of electric potential. We will now discuss about that. At the same, electric potential is nothing but a work or energy term. So regarding the energy concept of an electric field, we make use of potential. Now here is definition, just a small reminder. This is potential at a point or potential difference between 2 points, right? Potential at a point, you can see work done in moving a charge from infinity to that point, and this denominator is of course the test charge. Now here if it is potential difference between 2 points, here I am calculating, do remember, VQP. What is that? Potential difference between the point Q and the point P. VQP. This terminology is very different. Look here, VQP is nothing but Vp minus Vq, that is the work done in moving the charge from the point Q to P, and of course denominator the same, test charge, like this. And the SI units, dimension formula, everything, please look at your notebook. Now this becomes a very popular expression in electrostatics. Keywords: electric field, charge, moving between two charges, displaced between two charges. So any such keywords, immediately we'll use W is equal to VQ, where V is potential difference between the 2 points and Q is the charge that is displaced between the 2 points. This one. And another very popular concept would be the relation between electric field and potential. Remember, electric field is a conservative field. Therefore here the same rule that we have used in the mechanics, a relation between potential energy versus conservative force. The same here also holds good with a small change of symbols. Now here you will find V, the potential difference between 2 points, as E bar dot R bar, a dot product of these two vectors R bar. with of course a negative sign which has a significance. We'll discuss that significance. This is what is ER cos theta. Generally people are used to writing V is equal to ER. Of course we can make use of V is equal to ER for theta equal to 0 degrees or 180 degrees, but here please do remember it is ER cos theta. To understand that theta term and the significance of theta, now please look at this figure. Here I have shown an electric field which is of course a uniform electric field directed towards the right hand side, and I have noted 2 points. Suppose A and B are 2 points, and this is the line joining the 2 points, not charges, I'm sorry. A and B are 2 points, line joining the 2 points such that this vector now is what is R bar, and this is field vector theta. Therefore now I have to use V is equal to ER cos theta, not simply V is equal to ER, where R is the magnitude of the distance between 2 particles. And otherwise we have taken the result like this, which was the famous rule in mechanics. Ex, we are writing E as a function of x, right? Field is nothing but negative gradient of potential. This is what is the popular expression, you remember. Field intensity is negative of gradient of potential. And now let us come to 2 important points. What is the meaning or significance of negative sign? Negative sign shows that the electric potential always decreases in the direction of field. Potential decreases in the direction of field. To understand my statement one more time, look at the same figure. Now here A and B are 2 points. When you follow the direction of the field, A point appears first and then appears the point B. Therefore now A is at higher potential, B is at lower potential, like that. To understand it one more time with a small difference, see here one more electric field that I have shown here. In this case it is non-uniform electric field. Non-uniform electric field, just brush up your fundamentals. The density of field lines, the density of flux is represents the strength of electric field. In such case, now look at this example, A and B 2 points. You will find at A more density of flux and less density of flux at B. Therefore in this case, this is EA greater than EB. For writing this result, the concept is the density of field lines. Whereas now coming to comparison of potential at the points A and B. Now please look at these points A and B and be careful with this arrow mark. The data says is the field directed from A to B you can find. The arrows are towards A you can find, right? Therefore, in the direction of field, what is the meaning of that? Now therefore when we displace from B to A, it is the direction of field. A to B opposite to the direction of field. Therefore in this case our result would be VA less than V. VA less than V will be the result, because for that the concept is direction of the field. And one more time, in any electric field there can be points which are at same potential also. Look at this. This one is electric field which is uniform electric field in which intensity is same in both magnitude and direction at all points. Now in this field I show one example. Supposing I consider 4 points at the geometry. Supposing this one is A, B, C and D points which are forming a circle. Now in this case, let us apply the same significance of this negative sign. What do you observe? When you observe, A is the point that is appearing when we are following the direction of field. Therefore A is at highest potential and then C is at the lowest potential, right? Whereas now look at these points B and D. Now you will find that this is a line which is perpendicular to the field line. These B and D points are at same potential. Remember, A is at highest potential because it is the point which appears the first, and C is the point at the lowest potential for the point that it is appearing last. But these B and D points, they lie on the same normal drawn to this field line, the B and D are at same potential. Of course, now what will be the relation? I will write VA maximum greater than VB equal to VD, and it is greater than VC will be a correct inequality that we write. Now, this negative side also, let us make use in some examples. Supposing, what type of data, just I would like to show you here. This is, again, let me consider a uniform electric field which I have shown directed towards your right hand side. If this is what is the field, and suppose this is the positive charge. Yesterday's statement was the force on the positive charge is always along the field, and on the negative charge will be anti-parallel to the field. As a result, we can make one beautiful statement like positive charge always in the direction of field means, remember, it is the decreasing potential, right? And therefore, positive charge, the tendency is to move from higher potential to lower potential, whereas negative charge always tends to move from lower potential to higher potential. So that is what is a statement that we can make use of this negative side. Regarding equipotential surface, I request all of you to go through your notebooks, because about 5 to 7 points we have listed, and each and everything is a very important conceptual question. I would like to remind you all those expressions for potential in different cases. Now here, I am not doing all, but a few important potentials now I am just reminding you. First one is the point charge. Potential due to point charge. Q is the charge, R is the distance from the point charge. Then the expression is V 1 by 4 pi epsilon naught Q by R. Right. Yesterday we have told regarding intensity, which is a vector quantity. So whenever we are calculating the intensity, it is not algebraic summation. Whereas in the case of potential, which is a scalar quantity, potential due to positive charge is positive, potential due to negative charge is negative. Positive potential means higher potential, relative term. Negative potential means lower potential, like that. So potential due to positive charge is positive, negative charge is negative. In the case of any system of charges, 2 or n number of charges given in the geometry, the potential at any point, the net potential at any point, when we are calculating, please calculate individual potential. Potential due to Q1, potential due to Q2, potential due to Q3, so on. And in that, please do remember whether it is a positive charge or negative charge, and hence the potential also bear the same sign. Now finally, what will be the net potential means? We have to take the algebraic summation, like that. And one more important thing you remember, if net potential becomes zero, that zero potential point is not called a null point. Because in the intensity examples, zero intensity point is called as null point. Zero intensity never always means that potential is also zero, maybe or may not be, vice versa also. Even when potential is zero, intensity need not be zero. We have few examples which will now disclose that. Now for this is point charge using with the right sign convention. And then dipole also. Dipole, axial point it is 1 by 4 pi epsilon naught times 2p, remember p for dipole moment, and this is r square term. Every time I keep on telling you, please look at these relations. For point charge, if I write it as V proportional to 1 by R, for dipole it is V proportional to 1 by R square, right? So you will write V2 by V1 equal to R1 by R2 square, like this. So every time expression, keep looking what is LHS, what is RHS, constant terms and how they are related, which is changing and which is to be determined. A very popular scheme for CET and NEET exams. Now here axial point, we have given potential, and look at this interesting result. V equatorial point is 0. Why? You remember equatorial point is equidistant from both plus q and minus q. Therefore, at any equatorial point, potential due to positive charge is same as that of negative charge, and hence net potential becomes 0. Whereas intensity is not such case. Do remember, intensity we take vector addition, potential we take scalar addition. Therefore, V equatorial becomes 0. This is what is an example that you can look at. Potential is 0, but remember, yesterday's class we have given expression for intensity at equatorial point, which is non-zero. Potential 0, field is non-zero. An example. And one more very popular case would be a charged shell. A charged shell, again we have considered three different positions. One position is inside point, the other one is present exactly on the surface, and the other one is outside the surface. Here also we get a very interesting result that at any inside point, I would like to show this figure. You can look at this figure. This is supposing a shell and I charged it. This is a charged shell and this is the center C, radius I'm writing it as R. We know that all the charge resides only on surface due to expulsion property of the charge. And now this is some inside point. This is a point on the surface and this is some point outside. Likewise, I have represented there in the expression. Now, at any inside point, including center and just up to the surface, that inside point is same as potential on the surface. Any inside point, potential, same as potential on the surface. Therefore, this is an equipotential volume, you can say. So, Vi equal to Vs, the expression is, and this is 1 by 4 pi epsilon naught Q by R. Whereas for outside point, again, look at this distance from smaller, and this is the R taken from the center. Now this is again 1 by 4 pi epsilon naught Q by R. Same results we have told. A shell when charged, though the charge completely expels on the surface, but apparently it acts as a point charge, as if all the charge is concentrated at its center. And of course, I have shown a graphical representation. Not that this is the only graphical representation I am using for this particular. Every time, whenever you get any expression, you please try to draw a graph for that. What will be the shape of the graph? What will be the slope of the graph? What will be the area under the graph? Fourth one is what is the intercept of the graph, whether it is x-intercept or y-intercept. Different examples will make use of different concepts, either slope or intercept or area. Even we have discussed all these things in detail in the classroom. Even now, if you have any doubts, you please feel your liberty and call your teachers and clarify all your doubts. Right? So this one you can see, yesterday we have given a same kind of graph for E versus R. Now this is V versus R. E versus R graph was discontinuous. I hope you remember, right? Now this one is, you will find this is a continuous graph. This is a continuous graph, no discontinuity anywhere. And you will find that any inside point potential is same, and this is what is the maximum potential which is present on the surface or any inside point, right? And this is referring to the surface points. After that, the graph you can see is a parabola which says that distance increases, potential decreases. Show you some examples based on the simple results that we have discussed so far. Look at this first example I have taken. I have taken two charges, plus 4 microcoulomb and minus 1 microcoulomb. Unlike charges I have taken. Now, for this system, a question is asked like this. It's a wide open thing. Either find zero intensity point, which is called null point, or else find zero potential point. Zero potential point is not a null point, remember. Now here, we get zero intensity point for either system of identical, I mean like charges, or system of unlike charges. In either case, we get zero intensity point. We'll now explain that. Whereas, zero potential point will obtain only in the case of unlike charges. Now, it should be clear to you why it is so. Thinking anybody? Because just now we told potential to positive charge is positive and potential to negative charge is negative. So like charges means there is no question of any neutralization of potential, and that is why unlike charges only produce zero potential points. Now here, this is not a shortcut, let me tell you, because this one we have detailedly talked in the classroom, and that is why just I am writing the final result. Now null point, I have given an expression like this. The distance of null point is R, where R is the distance between the two charges. Suppose here I take it as some 18 centimeters, suppose I take it. D, the distance of null point is R, and in the denominator term you will see Q2 by Q1, and it is raised to half. Means it is the square root of Q2 by Q1. Now this distance is from the charge Q1. Now what is the meaning of Q1? It is not the order of charges that are given in the data. No. Q1 is the charge from which we need the distance. Supposing in this example, if you want the distance from 4 microcoulomb, then 4 becomes Q1 and this other charge becomes Q2. And in the other case, supposing I want to calculate the distance from this minus 1 microcoulomb, I will consider this as Q1 and this becomes Q2. Like it is not the order, remember. So now here it is D equal to R by root of Q2 by Q1 raised to the power half plus or minus 1 from Q1. The most important point is about the plus or minus. When we use positive sign and when we use negative sign. Positive sign for system of like charges. In the same, supposing it is 4 microcoulomb positive and 1 microcoulomb positive, then this will be used with positive sign. But now in the given data, it is like unlike charges, therefore I have to use negative sign. Second point. So it is zero intensity point, which is called as null point. We will get for both system of like charges and also system of unlike charges, such that it is either between the two charges or outside the combination, or the line joining only, either in between the charges or outside. Now, in the case of both like charges, both positive or both negative, in such case we get null point between the two charges, not mid and in between the two charges. Whereas unlike charges as shown in the given example, 4 microcoulomb and 1 microcoulomb, we don't get it in between. In fact, we get outside the combination. Now, whether we get inside the combination or outside the combination, two important things: that it always lies on the line joining the two charges, and second one is always closer to smaller charge. You understood? See here, 4 microcoulomb and 1 microcoulomb, minus 1 microcoulomb, the null point will be obtained to the right of 1 microcoulomb, because 4 and 1 only you have to take the magnitude. Supposing if it is given as 1 and minus 4, don't say that minus 4 is less than 1. It is not that way, consider only magnitude. Therefore, in this case, the zero intensity point, null point, will be on to the right of this 1 microcoulomb, minus 1 microcoulomb. So what will be the answer in this example? If I do calculate, this is 18 upon, it is, supposing I take this from 1 microcoulomb, then this is 4 by 1, both micro, therefore I need not use submultiple, and now I will write minus 1, right? So what will be the answer? So this will be under root, do remember please, Q2 by Q1 under root, therefore it will be 4 under root 2 minus 1. Therefore the answer is 18 centimeter. So what is that 18 centimeter point? Means, see, here you will get that null point where net intensity is 0. And if it is 18 centimeter from minus 1, it will be 36 centimeter from this 4 microcoulomb, like that. So it is either in between or outside, closer to smaller charge is a very important clue in finding the answer. Now the same with zero potential points. Now as you can see, zero potential point only in the case of system of unlike charges. Here you have unlike charges, therefore we can do that. Now for this, B is equal to R by Q2 by Q1 plus 1 I have written. Now here also there is a very important point to be noted. Again I am telling you, zero potential point, these are not shortcuts. These are, we have taken E1 is equal to E2 or V1 is equal to V2. We have just done 2 to 3 simple lines of simplification. Please go through your notebook, right? Now here, how to calculate this 3? Now this again, this is 18 by, suppose if I write 1 by 4. This time I am taking distance from 4 microcoulomb, that is, and then I am writing it as plus 1, plus 1. So this will be 4 into 18 by 5, 72 by 5 centimeter. 72 by 5 centimeter from 4 microcoulomb. Now please have this calculation. You will get a point somewhere over here. This is again a formula, an expression that gives you zero potential point lying between the two charges. Remember, this expression will give you zero potential point that lies in between the two charges, again closer to smaller charge, closer to smaller charge. Now, the answer is of course 72 by 5 centimeters, closer to minus 1 microcoulomb I have shown. But do remember, in the case of zero intensity point, on the line joining, there is only one possibility, there is one and only null point, zero intensity point. Whereas, if we consider zero potential points, we will get infinite number of zero potential points, which I have calculated only the one which lies between the two charges. Whereas, now, to the right, closer to the smaller charge, you remember that? According to that, now we will get infinite number of zero potential points to the right of minus 1 microcoulomb, satisfying the condition here. And now at the condition Q1 by Q2 is equal to R1 by R2. So any distances satisfying this condition Q1 by Q2 is equal to R1 by R2 becomes a zero potential point. Therefore infinite potential points will obtain, but null points we obtain only one. Do remember, on the line joining we are talking about. Now, one more numerical example I am showing you. We earlier told that equipotential surface, and a very important property that we have told, equipotential surface is always normal direction to the plane containing electric field, that is field lines. Now a geometry is given like this, and this is a planar surface. It is a x-axis, and they say this is y-axis. A simple question is created like this: x-axis. Remember, this is only axis. I am not telling you this is the field. This is only x-axis, and this is a planar surface, such that the normal to the plane makes an angle 120 degrees with the positive x direction. Is the data. Now the question is, what is the direction of E bar? What is the direction of E bar? Now remember, the concept is the plane containing electric field lines always normal to the plane of, normal to the equipotential surface. Therefore, any planar surface represents equipotential surface. We have told about the shapes of equipotential surface. So with that, this planar surface is an equipotential surface. Therefore, normal to this plane, I am taking normal to this plane. Now this is the normal. This is 90 degrees. This is 90 degrees. So now what are the possibilities? Now you see, supposing if this is what is E bar, this angle becomes 30 degrees with the positive x-axis. This is one possibility. Or else the other possibility, maybe in this direction the field may be existing. In such case, this becomes 30 degrees with the negative x direction. So we can say in general it is making an angle 30 degrees with the x-axis, either positive axis or negative axis, like that. And now One more thing I would like to remind you, the same which we have given expressions, potential due to point charge, potential due to spherical shells or spheres, like that. Now in this case, it's a very bigger drop, charged bigger drop. It's a drop and said it is charged drop, radius capital R supposing. Now this one is split into n number of small and identical small drops. So these are all small drops. The number is n. Now in this case, potential of the bigger drop is given and you are asked to calculate potential of each smaller drop. What will be the solution? Two things are the solutions. If we follow, we stated that V proportional to Q by R for a for a charged shell and for a charged sphere, V proportional Q by R, Q the charge and R the radius. Now here when you are splitting, charge is getting splitted because of identical, charge division will be equal. Therefore small q, that of charge on each smaller drop, now becomes 1 by n times the charge on the bigger drop. And another very important thing is that, you remember, this is a result, a popular one which you have used in first PU, second PU number of times. Bigger sphere into smaller spheres. In such case, capital R and small r, the radius of the smaller sphere related with this capital R is n power 1 by 3 times smaller. So now I am writing expressions for V small and V big. I will take a small division that this is the result. Remember, V small is V big by n rise 2 by 3. Suppose in this example I say V is equal to some 500 volts and n equal to 125. So what will be the answer? Yes? You did it right? Did it right? So it becomes 500 upon 125 raised to 2 by 3. So this is 500 by 25. Now don't call me for this 125 whole power 2 by 3 is 25. Hope you don't call me for that. So 500 by 25. So it will be 20 volt. Right? The key point here is potential expression that you have given for a spherical charged shell. Right? That is, and now similarly in this example, it always not only the potential but also examples on field also. In the same data, I will just not write, I will remind you. Don't use them as shortcuts. Please verify your notebooks, you will get the solutions. Now I am writing E small is E big by n rise 1 by 3. Remember. Similarly, if it is intensity, similarly I am writing surface charge intensity sigma small is also sigma big by n rise 1 by 3. Such results we have done in the classroom. Hope you will go through your class notebooks very thoroughly. Remember my slogan in the class notebook, word by word, line by line, page by page. This will definitely make you very confident about your, not only the concepts, but also on the calculations, simplifications, solutions as a whole. Hope for the last 3 days you have got around 6 assignments for all these topics. 6 into 60, nearly 360 questions I have shared with you. How many of them you have solved? How many of them you have gone through? Please make sure that you will finish all your assignments that are sent to you and you will find the ease in your examination hall. Stay home, stay safe. Thank you. Good day.